All right, how many people have taken a ride on a TU taxi?
Chris?
One? One? We only have one?
How many are there?
Is that like, is that riding in the Taylor University cop car or something?
No, they just distribute a bunch of yellow bicycles.
Yeah.
And then hid them off campus.
No. They after chapel, they released them after.
Oh, they finally put them out. Okay, excuse me. I wasn't at chapel today, so.
Oh, well, there you go.
Because I'm a sinner.
They said that like 2 months ago. They're like, yeah, it's all ready to go. They just went over where no one ever goes, and it was like, well, that was helpful.
Well, anyway, they released them, so. I know Lindsay used them because she just about ran me over, and she was, you know, like in some kind of an urgent rush to get out of the chapel. What's that? She was riding a TU taxi.
She walked with me after chapel. So.
It wasn't her there?
No.
Okay.
Oh, there are two.
I don't know.
Lindsay has a twin?
A master and the apprentice.
All right. Okay, so I think we're finishing up.
What a loser. You say loser.
All right, gardening. Okay. We talked last time about TTT diagrams, heat treatment. Okay. So now we're going to talk about how we're going to use these TTT diagrams. So the process of using them is twofold. One is to strengthen material, and one is to remove, to put in characteristic microstructural features, and one is to remove those microstructural features. So today we'll talk about putting them in, which we call heat treatment. On Wednesday we'll talk about annealing, which is the process of removing those features. Okay, so there's several different kinds of heat treatment. The first we're going to discuss is tempering. So, if you look at the TTT diagram for eutectoidal steel, which is shown up there, which we drew before, we talked about the fact that if you can miss the knee in this curve, right, you can cool it fast enough down here, you can get through these martensitic transformation temperatures, right? And the 90% line was 130 or so degrees. So if you quench it down to room temperature quickly enough, then it's more than 90% martensite, more than the 90% of this brittle, body-centered tetragonal structure. Okay, I don't know if I mentioned last time that it was brittle, but body-centered tetragonal is brittle because it just does not have the same number of slip systems that FCC does. Yes?
Does it have to be from liquid, or is it just from something?
No, this was from gamma, remember? It was quenched from gamma up here.
Okay.
From the eutectoid composition, or the eutectoid temperature rather. So we're quenching from 727 down to room temperature. So you really are only going to be able to do this with very thin pieces of material. Right? Because anything that's thick, you're not going to be able to get this kind of time scale and get the heat extracted from the inside of the thick material. So really we're talking about doing this with thin things like, oh, I don't know, razor blades. Right? So razor blades would undergo this process.
Or swords.
Well, we wouldn't do it with the whole sword. You don't get the edge.
Tempering?
No, martensitic transformation. You couldn't get the whole sword to transfer to martensite. You wouldn't want to, because then it'd be a brittle sword. You hit somebody once, whack, shatters. It's all gone.
But then you temper it, but then you heat treat it.
We're going to do the heat treatment, so you can be quiet now and just let us continue the class.
Why do you want the blade of a razor?
Martensite? Martensite is because martensite is brittle but very hard.
That's a katana.
It's an extremely hard material.
Hardness is just like you just kind of poke down with the thing and then.
Yeah, you poke it with a pin. Right, you poke it with a pin, it doesn't make a dent. That's hardness, right? So we want hardness for a razor blade, right? So when you hit a whisker, it doesn't dent the blade, right? You want a nice sharp edge, right? So you want to. So martensite, you make your razor blades, you quench them down past this knee to a martensite. And you can do that with a nice thin piece of razor blade.
If I took a hammer to a razor blade, it'd shatter.
Has anybody ever tried to take a razor blade out of a razor and bend it?
Yes.
Yep.
Okay. You'll,
Like a face shaving razor?
like one of the thin face shaping razors, yes.
Yeah, you can
I've
bend
done it
it.
with like the box cutters where you have to snap it.
I actually just bent mine like 3 days ago on accident.
I'm not sure how you do that on accident.
Really tough hairs.
Apparently so. Tough beer.
I was
Did you
pulling
see
it out
it?
of my bag and it caught on something.
Okay, well, you'll find that razor blades are typically more likely to behave brittle. So they will bend, but you can actually snap them easier than you can an equivalent piece of metal, of just untempered steel. Okay. Because, again, the idea is to transform down to martensite so that they're tougher and harder and better, shaving your
Is
beard.
that generally how things work? Like the more harder you get, the more brittle it'll get
Yes,
for a
generally speaking, right. Particularly within a classic material. Anyway, but now this stuff down here, this stuff down here is really brittle. Right, the martensite is really brittle. And so if I really have quenched it down to that condition, I could actually, it won't bend much. Pure martensite won't bend much. It's a very brittle material. So what I want to do is I then want to bring it up and heat it a little bit and bring it back down. So I heat it up above the martensitic start temperature. Probably don't even have to heat it that far, honestly. Okay. So,
I thought these graphs didn't work for heating things.
well, it doesn't show you, it won't convert to bainite,
Oh,
Right.
okay.
but it shows you what you're doing in terms of the temperature and time. Okay. So that you can't pay attention to what the microstructure is going to be
Okay.
for going up, but you can still do it. What happens up in here is I form Fe cementite particle. So that the cementite that is captured, or I'm sorry, the carbon that is captured down in the BCT material, which is stored, I'm trying to remember, the carbon sits at in the middle of the edges. Okay, the edges of the crystal. They're octahedral interstitial sites in the FCC lattice, yes.
I can't remember the terminology for it, but the 3 lines, the 1%, 50%,
Right.
100, is that to the right of the 100%
Yeah,
line?
so, yeah. So
Okay.
it's like this.
Okay. Just any spot past there.
Yeah, so you just go, the point is actually, once you've quenched it down here, you can raise it back up again.
Okay.
You know,
And then-
once you're down here, you've undergone the transformation, raising it back up here or there, doesn't matter.
Okay.
So it's just that the reality is, you notice that's this time frame here is sort of like an hour-ish.
Okay.
So, it's just, usually you quench it down, you do a bunch of parts, then you come back and you
Okay.
warm them up to temper them. You don't do it immediately, it won't
Yeah.
cool.
And that goes with saying that like the material properties only applies when you're cooling into them. Like if you're going back up, it doesn't mean it's 1%, 50% or.
Right, doesn't have any meaning. But what happens is, as you warm it up, you now create additional thermal energy to allow for diffusion. So now, the carbon and iron can diffuse and form little cementite particles, because remember, at the eutectoid composition, down here at room temperature, we're down in this bottom range down here, right? The stuff wants to be alpha plus Fe3C. Right, that's what the steel wants to be, is a mixture down here of alpha plus Fe3C. So if you do that, you're going to form these little Fe3C nodules or particles, and those particles can form to relieve the internal strain that exists in the martensite. Remember when I talked about the martensite being quenched, it went from FCC to BCT, right? And as a result, there's a strain in the lattice. The lattice kind of shrunk in one dimension, but it's strained. It doesn't want to be in BCT at room temperature. Okay? So what happens is you heat it up, and it allows that strain to be relieved by forming these Fe3C particles. Everybody's funny. All right. And then what happens is, depending on how big the particles you want, how big of particles you want, you leave this here for an extended period of time before you quench it down. So you quench it down based on how large you want the particles to be. If you want a fine distribution of small particles, then you quench it more quickly. If you want a larger distribution of larger particles, then you quench it later. The longer it stays up here, the larger those particles will grow. Those Fe3C particles. Okay? And so what happens is, the strain relief allows you to have regain some measure of ductility in the martensite. So this would be tempered martensite. The thing you would end up with out here is tempered martensite. Okay. So in this case, we've actually softened the material a little bit. We've returned some ductility. But we do so by changing the nature of the microstructure.
All right, so which step is the tempering? The initial first cool, or the bringing it up to temperature and then cool more slowly? Which?
Tempering is the whole process.
Oh.
Okay.
This is how you make the brick glass.
Generally speaking, this is the tempering piece. That's a quench, this is a temper. Okay. But the whole thing is tempering. This whole lump here is tempering. Okay?
This is how we would make tempered glass.
What's that?
This is like this same.
No, tempered glass we already talked about.
Oh, yeah, we did.
We already had a discussion on tempered glass.
But is it all like similar? Like, it's just the idea of tempered, the concept of temper is similar with the process to get to it.
The process is the idea of doing the sort of heat treatment
Okay.
to adjust the properties the way you want them. That's tempering. Okay. Any other questions? Okay. Now the problem we have is if you do this curve right here, quench it from 727 down to room temperature, you're likely to cause the thing to shatter. Because once it forms martensite, it's a very brittle material, and continued quenching rapid quenching is going to cause these great thermal stresses. We talked about thermal stresses before, right? Where the outside is stressed in a way that the inside is not. And the outside is the brittle material, and the inside is not the brittle material, then we create tension in that outside material, cause cracking. You guys remember that process when we talked about it for glass? Same thing happens here for the martensite. So what you're more likely to do is you're more likely to use mar tempering or mar quenching. For that, we will go to blue. So mar tempering or mar quenching is where we take this curve and we just miss the knee, and then we can leave it out here for a bit and then gradually cool it through that region. So the purpose of the quench is just to avoid the knee. And you only quench it as far as you need to avoid transforming the material, to avoid the initial transformation of the material. And then once you get the material down here, you can gradually cool it at a non-quenched rate and still get it completely formed into martensite.
So what's the advantage of that?
The blue line?
Yeah, it's like the 90-degree, but besides avoiding the 3 lines, is it just so you don't shatter the material?
Yeah, so it's just to avoid shattering, because this is an addition, you don't have any martensite formed here, right?
Yeah.
So there's nothing to shatter until you start forming martensite. So you go through that part of the quench slowly, so that you allow things to equilibrate better, as opposed to quenching all the way down through here, so that once I start forming brittle material, now it's brittle and can shatter. Okay, the shattering would occur down here someplace. This allows you to go through there more slowly and more gradually. And then you can follow that up with the same tempering process afterward. Okay, this is just done to avoid cracking due to the quench. Okay. Because in reality, if I draw the surface is going to quench like this, the inside is going to quench more slowly. Right? There's going to be a difference between the surface and the inside. So there's going to be a point in time, in this interval of time, the surface is brittle, but the inside is not. And so again, that's where the shattering comes from. Everybody kind of see that? At any time, any of these times, right? The surface is brittle, but the inside, well, except for the last one. The inside is not brittle, and so you end up with this thermal contraction issue. Right? The outside is contracting, the inside is not contracting, so the inside is pulling the outside apart, causing the brittle failure. Okay. So Mar tempering, Mar quenching is like that. Then the other possibility, another possibility, is Aus tempering. And Aus tempering, getting too many lines on here. Okay. Aus tempering, again, avoid the knee, but then you can just basically let it all completely convert to bainite, but just barely above the martensitic transformation. So you get as fine a bainite as possible, and then bring it down. So Aus tempering generates basically the finest possible bainite by quenching to just above NS. So the idea here is, let's see if we can get 100% bainite in our material. Remember the difference between bainite and pearlite? Yeah, that's great.
Bainite it's not like.
Bainite is, it's not like, yes,
not
correct answer.
structured, but it's kind of like all.
Right, the kind of randomly oriented, the lines are kind of randomly oriented. Whereas in pearlite, even fine pearlite, the lamella are still straight. So you can get a dislocation can propagate all the way through one of those lines. Right? So pearlite, a grain looks like this. Even if it's fine pearlite, I can get a dislocation to propagate all the way through that chunk of alpha material. Therefore, it's going to be more likely to deform. Whereas with bainite, because these are oriented in random directions, the only way I can really get it to be random is close my eyes so that I don't see what I'm doing. Okay, so now they're in random directions. If I start out with a dislocation here and it wants to propagate, it's going to get pinned by an Fe3C layer. And it's not going to be able to propagate through the Fe3C layer. So this is stronger than that. It's less likely to deform, therefore has a higher strength. Yes?
So with all these different things, kind of like quenching it to a certain point, whatever, do you just have like a temperature probe in/on your material? You say, oh, look at the temperature, pull it out, or are you like, do you put a specific temperature of water to get it to quench to a certain point? I'm just trying to figure out
How do you do
how you
it? Generally quench in oil, not water.
Okay, so you,
Water boils, right? So you're going to quench it in steam, right? Because all of this is above 100 degrees C.
okay.
So you generally quench in oil or some other kind of medium like that. Something that doesn't
So
boil.
the striped sample there is pearlite, right?
That's fine pearlite, right? That's the stuff that you form up in here. So there's coarse pearlite, fine pearlite, bainite. So Aus tempering just means form the finest possible bainite you can. Because bainite has a strong, but get 100% bainite. So you still have to quench it down and come across. You can't just do a slow quench because once you start up here, you're going to form coarse pearlite. right? And if I quench down to here and then carry across, I get fine perlite. But I've got to quench it all the way down to here and then let it completely transform into bainite. Does that make sense? So this requires a great deal of control. You've got to get it down past the nose, but then keep it at that temperature. So you got to get it to that temperature quickly, but then keep it there for a long time. Well, hour or two. Okay, so in other words, you can't just take your thing and throw it into a mold or throw it into a vat of something. You've got to keep it at the right temperature. Okay. Okay. So, in terms of characterizing the performance of these things, the way that we, I don't want to use that. The way that we characterize how different quenches behave in terms of the material properties is use a process called a Jominy end quench. So take a Jominy bar, which is nothing but a 1 inch by 4 inch round bar, and oftentimes there's a flat machined on the top surface. Okay, so it's a round bar with just a flat surface on the top. And again, 1 inch diameter, 4 inches long. And what I do is I heat that thing up to a particular temperature, to some kind of austenizing temperature. So remember, gamma is called austenite. So an austenizing temperature is anything above 727 if it's eutectoid steel, so that I get it up to be pure gamma, and let it sit there for long enough to get completely transformed. Okay, so the first step here is to austenize. Okay, so at a temperature greater than 727. So I have purely gamma material. And then what the second step then is to apply a water spray to one end. So I spray water at a very high volume to one end. So that what happens is the very end of the bar quenches almost immediately down to the water temperature. See that? So I'm spraying 70-degree water at the end. The front surface almost immediately goes to 70 degrees. And if I plot the cooling rate as a function of position, d, the distance from the quenched end, I get something that looks like this. So I get a high cooling rate for this end. So this end experiences a rapid quench. But the bar end, right, so if I put on here 1, 2, 3, 4, 5, etc. So 1 is going to be right here, 2, 3, 4, 5. Okay. So then I'm going to redraw this. So looking at my TTT diagram. Reasonable. Okay. Then what that says is my first curve, my 1 curve, probably will miss this thing. Right, that's going to be 1. Probably going to miss the nose. You notice I draw it in a curve format because this is a log time on the horizontal axis. Right, so the cooling rate is linear. Right, the temperature is a function of time, it's a linear rate, but it shows up as a curve here. So 1 might look like that, 2, 3, 4, 5. Right? 2, 3, 4, 5. Does that make sense? So I get different cooling rates, therefore I go through the different curve at different points. And if I then came back and plotted hardness as a function of D, Rockwell C hardness, and we talked about hardness, resistance to an indentation, I get something that looks like this. High hardness on the front end where it was quenched, low hardness in the back end where it wasn't quenched. So I can determine what, based on the geometry end quench for my particular material, I can say, well, I need a hardness of at least this much. Therefore, I know what kind of quench rate to use to get my stuff to be that hard. Right? And hardness is correlated to tensile strength. So if I know the tensile strength of the material that I need, it's got to be here or above, then I know I have to have, so in other words, let's say that this is 1, 2, 3, 4, 5. So I know that I've got to be at cooling curve 3 or above if I want to reach that, achieve that hardness.
So R is hardness?
R is Rockwell hardness. Yeah, Rockwell C hardness. It's one of the hardness scales. Your book also talked about Brinell hardness. It's another scale. They're just different. They're empirical scales. But the point is, if I know what hardness I want to be at, or what strength I want to be at, then I just have to stay at a quench that's faster than that. Yes?
What if you had a different cooling rate? On the plot in the book it says that 700 degrees Celsius per second.
Yeah.
So what if you cooled it faster? Or
Well, that's what I'm saying. That's what you get by squirting this thing with the water.
Specific.
You get a specific starting point in distribution.
Okay.
If you wanted a faster cooling rate, you'd have to use colder water or more larger volume of water, or some kind of.
So this is just for a very specific case.
Well, the maximum is a very specific case,
Okay.
and then depending on where you are along the depth, you'll get everything below that.
Yeah.
The maximum cooling rate is determined by the nature of what you're spraying, how fast you're spraying, and all that. Okay. Any other questions about the end quench? Okay. So, so this is how we end up sort of turning what's happening into the stuff we can use, the strength of the material. Okay. And then you can do actual microstructural analysis to go in and look at each one of these samples and see what the microstructure looks like, to see what's a coarse pearlite, what's a fine pearlite, all that kind of stuff. Okay. So there's one more kind of hardening that we haven't really talked about here. This is all using eutectoidal compositions. Right? So all of these are using compositions between 0.02% alpha, 0.02%, which is the peak of the alpha, and 0.77%. Right, so these are all for low carbon steel. But there's also the possibility of doing precipitation, doing hardening for things that don't go through eutectoidal composition. So I'll sort of zoom in here so you can see it. But what if we have, remember from the lead tin, not that we're going to do tempering of our lead tin system, but I remember had this on the left. What if I, instead of having, and then we had a eutectoidal composition, or eutectic composition out there for lead tin, I can actually do some tempering on matte line as well. So I have a material that's not going through eutectic. At this point, right here, what's the microstructure look like? Remember, this is, well, I'll just call it liquid plus alpha, alpha, alpha plus beta, okay, for lack of better definitions. What is the microstructure going to look like at that point? It's alpha, what's it gonna look like? And what am I gonna see?
It's gonna look like crystals of alpha.
Right, a bunch of grains of alpha.
Great.
Right, so at that point, I just have a bunch of grains of alpha. Okay? What do I have here? Oops. What's that look like down here?
Alpha with beta and the green boundary.
Right, so here, I'm gonna get the same idea. But I'm gonna get a lot of beta forming at the grain boundaries. Right, so we get grain what's called grain boundary decoration. Right? So what I can do is, but the problem is, from a strength standpoint, this doesn't help me at all. Because now all my beta's at the grain boundary, I can still propagate dislocations across this alpha without anything stopping it, other than the normal strengthening mechanisms of interference with dislocations or dislocations running into impurities or whatever. But there's a lot of space for the dislocations to propagate. So this really doesn't strengthen this material is not stronger because the beta is not doing anything to stop the deformation, the propagation of dislocations. So what I'm going to do is I'm going to bring this back up to a temperature just below where the alpha forms, or where it all dissolves back into alpha. Right? I'm going to come up to this temperature, and then if you can imagine my temperature curve now, let me erase all this so I can put the temperature curve on there. I'll put my lines across here. So I'm going to take now, I'm going to heat something up to the top temperature, get it all converted to alpha, right? Then quench it back down to the region where I care about, there. And then I'm going to bring this back up and heat treat it at a temperature just below the point where it goes back to being pure alpha. So when I heat it, bring it right up to here, right up to that borderline, right? All the beta is going to be reabsorbed. Right? Does that make sense?
Into alpha?
Into alpha, right? Because the alpha concentration becomes more B-rich. Right? Because the alpha that's here has this concentration of B material. When I get right up here, just below that, now all the beta at the green boundary is just going to be reabsorbed back into the grain, so I have just the alpha grain and just a little bit of driving force to form beta. But I stay there a long time. Right, this time here, I stay there for a long aging time. T sub aging, aging time. Okay? Subscript. So I stay there for a long aging time. What's going to happen is that I'm still just below it, so the beta wants to come out. But I'm staying there long enough that beta can come out wherever it wants to. It doesn't have to just happen at the grain boundaries. And so what happens at this point then is my alpha right? I start to get beta forming out in the middle of the alpha grains because I just get tiny little bits forming. And so I don't have to worry so much about diffusion driving the process because there's so little of the bits there's so little of the bits that are forming beta that I don't have to diffuse large amounts of B material, whatever the B material is, someplace to get the beta to form. Over here, I got to form so much beta that it's all got to form the green boundaries because I got to bring lots of B material. If this is lead tin, I got to bring lots of tin over to the grain boundary regions, and it's a lot easier to bring the tin along the grain boundaries because the diffusion pathway is much easier. But here, I just have to, just a little bit, if I have 3 tin molecules, or 3 tin atoms, that are next to each other. We can call that a grain. We will start working from there. You kind of see what I'm saying? So they end up forming these things all over and getting this this sort of speckledy look. Okay? And then I quench that down. What's going to happen is those grains then are going to be, those locations are going to be locked in.
And then beta will start forming at those sites.
So I'll basically have formed beta at all those sites in the proper proportion in order to, be at equilibrium. Does that make sense? But what happens is, if I leave that there too long, these kind of coalesce into individual big spots instead of being the tiny little spots. And now you can imagine the tiny spots are gone. I don't have time to go back and erase. Okay? You see what I'm saying? If I leave it up at this temperature too long, even those tiny little spots will eventually congregate together because they really want to be together. And so, if I plot the hardness as a function of aging time, and again, hardness here. If I age it a little bit, I get an increase in hardness. Right, so I'm moving from this structure to the polka dotted structure, but then if I overage, it actually softens the material. Because now even the grain boundaries aren't good. Now I don't even have beta at the grain boundaries, so I have these beta chunks. And the beta chunks interfere with less of the dislocation motion than the beta grain boundaries.
So if you're doing it the right way, will you still get beta at the grain boundaries?
You'll still get, yeah, you'll still have it at the grain boundaries. You can't avoid it, but the point is, you'll do it by being staying right here, just below that temperature. Then you enhance the opportunity to achieve beta anywhere uniformly in the material.
But the thing is that at that point, there's not that much drive for there to be beta at all.
Right, so they're just tiny little specks. But as I cool it down, those tiny little specks now having nucleated will grow. Does that make sense?
Is it quenching to bring it down, or is it just kind of cooling it?
It's a yeah. It's not really a rapid quench or anything because the I suppose if you did a rapid quench, you might not get full conversion to the equilibrium concentration. Right. If you quench it down far enough, fast enough, then you may not get an actual alpha beta distribution that you're supposed to have, because you inhibit diffusion of the B material to even form more beta. But the point is just that there's a target here. I want to get this peak. That's what I want to get. I'm going to call this process precipitation hardening. Because we're forming these precipitates in the matrix that, again, serve to inhibit the motion of dislocations. And the more uniformly distributed inhibitions you can get, the stronger the material. But if you allow those inhibitions to coalesce into large chunks that are not uniformly distributed, then the dislocations can propagate between them without constraint. And so you've softened the material beyond where it was to begin with. Okay? Does that make sense? So those are the several different ways of using the TTT diagram to harden your material. Now let's take a look at a question up here on the, does anybody have any questions before we move on to the problem, the example problem?
So
Okay.
we're starting with our, the lines where you go up to alpha and then down.
Yeah.
Is that like the temperature that you're starting at?
So this ladder plot here
Yeah.
is, yes, this is a plot of temperature versus time for the aging process. Okay. So you take it up to the alpha range, leave it there long enough to make sure it all equilibrates to alpha. Then you quench it down so it's stuck as alpha. right, to the bottom temperature, and then you bring it back up to the point where it can just begin to form beta, but allow it to form that. Now, the other thing you can do, and I didn't mention it here, if I cold work it in between, if I actually deform it a little bit in there, so I somehow beat on it or shot peen it or just somehow make some deformation, then when I raise it back up, the location where I have deformed it, where I've piled up dislocations in the microstructure, is where the beta will likely begin to form. That the deformation will serve as a nucleation site for subsequent beta formation. Okay, so there's other things I can do in here, in this time frame here, to actually accentuate the distribution of beta particles that I want.
So that really fast drop is, so we're quenching it so that it's just all alpha?
We're quenching it so that it is room temperature, all alpha at room temperature, which is not supposed to, assuming we're quenching to room temperature.
Right.
Or we're quenching it down there so that we get below, it's kind of the same thing, as, there's going to be a similar kind of a knee.
Right.
In that there's a diffusion and nucleation driving force for the formation of beta. And if we get down below that, then we can prevent any beta from forming because there's just not enough thermal energy to cause diffusion. Or we can minimize the amount of beta that forms at the green boundaries. And then bring it up and gradually do it so we have more control over where the beta forms. Any other questions? Okay, I know that's kind of qualitative, but again, that's the nature of the class. Okay, we have a eutectoid steel that's cooled at a steady rate from 727 to 200 degrees C in exactly 1 day. So we take 1 day to gradually cool from 727 down to 200. And the way you would do this normally is you would leave it in a furnace and you would gradually dial down the temperature of the furnace from 727 to 200. Okay, because you can't really have a controlled cool otherwise for this long period. So superimpose this cooling curve on the TTT diagram of figure 10.11, which is shown below there. So what do you think that's going to look like?
Just a line from the left edge at 727 all the way down to the 1 day mark on the right edge.
Straight line? If it's a constant cooling rate?
Yeah, it's
No, it's a curve because it's on a long scale.
Right, it's on a log scale, so it's going to be curved. So I've taken the liberty of showing such a curve. There it goes. So that's what it does. Everybody see that? And that was nominally done in real time. So the curve rapidly, if you go, so you go again, you watch how rapidly, right? It very quickly gets over there to the 1 hour time frame. And when, it's obviously accelerated. Okay, but nonetheless, that's roughly the speed at which it happens, right? So very quickly, within an hour, it gets over there and does conversion, right? So from result of that plot, what temperature, determine what temperature would a phase transformation first be observed?
727 almost.
What's that?
At just under 727.
so like 720, 718. But it's
So- Right there. Right, that's the point where we first observe a transformation.
where?
The red dots.
Up again,
Oh, wow.
right there.
Yeah, that's,
Okay.
Yeah.
So probably 715 or something.
it's 17, but.
You guys can bounce around a little bit on your.
What would be the first phase to be observed?
For the Y? That says it is?
What would be the first phase to be observed?
Coarse parallels.
It would be very coarse perlite, right? And that's the very high end of the coarse
It's
perlite.
like,
And remember the observation, the approximate nature of using an isothermal diagram to represent a continuous cooling process after transformation initiates. So like I said, this is down into the, this whole thing is supposed to be sort of down and to the right. And the way that we kind of consider it is that we identify the place where it starts to transform. And then unless we quench from there, we consider that that basically forms all of that material. Kind of do an isothermal approximation. But here, you go through the diagram pretty quickly, right? So it's all gonna be coarse, very coarse pearlite. Does that make sense to everybody? Okay, part D, repeat A through C for a steady rate of cooling in exactly 1 minute. So let's, D says 1 minute, E says 1 second. Okay, so what would that look like?
But what did we answer for the first part though?
The temperature at which it starts and what it forms. Temperature is 717 apparently, degrees C, and it forms coarse pearlite. So for part D, what do you think that curve is going to look like? It's going to go more quickly, right?
Where does it say? I don't see a time.
For steady state, repeat A through C for a steady rate of cooling in exactly 1 minute, as opposed to 1 day.
I see.
Okay? So now we're quenching from 727 to 200 in a minute. Okay, so that's something like taking the thing and if it's a plate of steel, putting it in the air, right? It's probably going to, just pulling it out of the oven and putting it in room temperature air is probably going to represent that kind of cooling rate. So, there's that curve. Okay, that makes sense? Part B, what is the temperature at which the phase transformation would first be observed? What's the temperature at which it will first be observed, approximately?
671.3.
4.
42. Okay, so right there, in the neighborhood of 670.
679, or 669.
Okay. And what material is going to be formed? Still coarse pearlite, right? Still going to be the same coarse pearlite. Okay, now let's repeat it for E. For a cooling rate of exactly 1 second. What do you think is going to happen? We're going to miss the knee. Right? It actually starts off here to the left, because notice this is a log scale, so this is 0.1 seconds. So in the first tenth of a second, it already dropped from 727 down to 670. Okay. So we completely missed the knee. So what is the phase transformation? What is the first phase to be observed?
EMS, the Martin site.
The first phase to be observed then would be Martensite. Because we miss the knee, we don't get any of that stuff, we only get Martensite. So you realize the only way to get bainite from these curves is to quench rapidly, like 1 second, down to a temperature just above M sub S, so like 250. And then allow the material to then cool over a long period of time. Right? The only way to get bainite is to quench past the knee to a temperature and then let it cool at that temperature.
If you go right at the knee, that's still kind of coarse.
Right, if you go right through the knee, you're going to get fine pearlite right at the knee. Yes?
Could we go back to the 1 minute? Because I have a question about why, like, so, okay. So what if a curve went sort of right, like there's 2 knees, right? What if it went right through the middle of those so that it never reaches past the 100% line?
So basically, if we had a curve that went like this,
Yeah.
then its furthest intrusion, so in other words, if it goes, let's say it just kisses off the dashed line, then we'd say we have 50%, medium pearlite, somewhere between coarse and fine, whatever this area is, right? And then the other 50% would be transformed into Martensite. It's the equivalent of basically this is the equivalent of this process.
Don't you go from where it first enters though?
Yeah, so what I'm saying is, if you go like this.
Oh, because it enters at some almost coarse pearlite.
Right, it enters here and it hits 50% there, so essentially we've got this, but only 50% of it that. And then the rest of it's down here at Martensite. Okay. So So you basically track the furthest intrusion that you get for your percent transformation. All right, we are out of time. Next time we'll talk about annealing.